Exercise 2. Let A be a ring and then we are going to study this ring polynomial. With one variable, one indeterminate x, coefficients in A. We're going to study this ring. First question. To prove that F general element of AX is a unit if and only if A0 is a unit and all the A1, An are nilpotent. In other words, the nil radical of A. Firstly, we could just prove by just stupid way, but just recall by writing down to those computations. So if F is a unit, then there exists B0, B1x, Bmx to the power m, such that times G equals identity, which is 1ex. And this further implies B0 plus A1x to An to the power n times B0 plus B1x Bm to the power xm equals constant 1. But then this further implies obviously A0 times B0 equals 1. And then you look at degree 1 coefficient, A0 B1 plus A1 B0 equals 0. Similarly, A0 B2 plus A1 B1 plus A2 B0 equals 0, etc. Finally, the highest degree, An Bm equals 0. Okay, we're going to just use these conditions here to deduce. Actually, there is a hint. By induction on R, try to prove that An to the power R plus 1 times Bm minus R equals 0. Obviously, here is the hint that for any R less equal than m. Right, this is not difficult. A0 B0 equals 1. Obviously, it's more easy to start from here and to the upside. Let me write down. So An times Bm equals 0, and then you have An Bm minus 1 plus An minus 1 B m equals 0. This is a degree. This is a degree n plus m. This is degree n plus m minus 1. And so, in particular, if I time An on both sides of this, I got An squared times Bm minus 1 equals 0. right? Because an kills bm, and so I'm time an on both sides of this equality. What is only left is here. Similarly, let's write one more term. an bm minus 2 plus an minus 1 bm minus 1 plus an minus 2 bm equals 0. Similarly, just by time an square on both sides of this, you got an square kills bm minus 1 kills bm. What is left is only bm minus 2. And then you just use induction, you got it to the power r times b and minus r equals 0. But a0 b0 equals 1. Finally, for r equals m minus 1, you got an to the power m minus 1 b, for r equals m, n to the power m times b0 equals 0. But this is a unit, and so an is nilpotent, right? And then how do you do? If your f equals a0 plus a1 x plus an minus 1 x to the power n plus an x to the power n, and this is nilpotent, then the left one is nilpotent, because this is saying that this is in the nil radical of x, and this is an ideal, so it's preserved under addition, f minus an x to the power n. So this is in the nil radical, this is in the nil radical, and so this is again the nil radical. And so similarly, you can use induction to show that the highest degree of this, which is an minus 1, is also in the nil radical of a. So use induction, you show that a0 is in unit of a, and all the a1 till an will be in nil radical of a. Conversely, it is obvious. If f equals a0 plus a1x plus an to the power x to the power n, if each an is in the nil radical of a, then each an x to the power n, or a j x to the power j, is in the nil radical of a, and so is their addition, because this is an ideal, in particular preserved under addition. And so this is of the form a unit of a ring plus nilpotent element of a ring. So this is the unit again. This is showing the converse direction. Or if you want, by last exercise. Second question. F is nilpotent if and only if all the AI are nilpotent, which means f is the nil radical of ax, if and only if those are in the theoretical of A. Firstly, we could just prove this by direct computation again. Obviously, this is trivially true, as we said, because theoretical is an ideal. If your A0 until AN are all in the theoretical of A, it will tell you that A0, A1x, A2x squared until AN x to the power n are all in each in the theoretical of AX, and so is their addition, which tells you F is there. Conversely, if F is in the theoretical, how do you show that each term is there? So that's just the first method, which is just by computation. A0, A1x. Let's write it down. So there exists some big N such that this equals 0, right? So first, obviously, this tells you that AN x to the power, this is the highest degree, this is 0, and this tells you that AN is 0. This is in the theoretical of A. Suppose we, or in other words, let's use induction, okay? Suppose 2 is already true for any F with degree less equal than n, and we will want to show a G with degree G equals n plus 1 satisfies 2. Well, when y means 2, I'm only in one direction, which is nilpotent implies all the coefficient nilpotent, right? So suppose our G is b0 plus b1 x until bn x to the power n, then bn plus 1, n plus 1. I'm going to use induction. So in this case, G to the power n equals 0, similar as what we have discussed, tells you bn plus 1 to the power n equals 0, tells you bn plus 1 is in the theoretical of A. But then it tells you that G minus bn plus 1, because this is in the theoretical of X, and G is also in the theoretical of X, tells you that the addition, this subtraction is also in the theoretical of X, but this has degree n, tells you that all coefficients of this G minus bn plus 1x to the power n minus 1 is in the theoretical of A. But what are the coefficients? Tells you that A0, A1, or B0, B1 until Bn. Another method, which is more I would say enlightening, would be to notice that F is in F has all coefficients in the theoretical of A is equivalent to F bar equals 0 in a quotient I x for any I prime ideal of A. It is because the intersection of all the I prime is the nil radical of A. Is the nil radical of A. And so if all the coefficients are in the nil radical of A, then in particular they are in all the prime ideals of A. In particular, the quotient of f would have 0 coefficients in the quotient ring. Conversely, if f bar is 0, which means this coefficient is contained in I for any prime ideal I, conversely tells you that the coefficients are in the nil radical of A. Right. And then if you notice this, what we have to do is just to redescribe this f being nilpotent, to prove f is nilpotent if and only if f bar equals 0 in a quotient Ix. How could we prove this? To prove this, you just have to notice that